Hi and welcome to John's Maths book. In this video, we're going to be looking at Simpson's rule. If you like the video, then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. Simpson's rule is a numerical method to approximate the solution of a definite integral. In some circumstances, we come across functions which cannot be evaluated using standard techniques. In these circumstances, we can use a numerical method which approximates the area under a curve between 2 points on the x-axis. So let's see how Simpson's rule works. I've sketched a continuous function f of x, which is defined across an interval of ab. Using this method, the area of the function is broken up into an even number of strips. A parabolic approximation of the area is done across pairs of strips, and the approximate area calculated for each pair is summed to give an approximation of the total area. The greater the number of pairs of strips, the better the approximation. In the sketch, I've chosen to use 2 pairs of strips, so 4 strips in total. Let's drill down into a pair of strips and take a look in more detail at how this works. I've extracted the blue shaded area, which contains 2 strips. Note we need 2 strips, as the formation of a parabola requires 3 data points. The parabola is an order 2 polynomial of the form shown here as f1 of x equals a0x squared plus b0x plus c0. The parabola is formed between the points shown here, here, and here. The dark green curve here represents its shape. The area under the parabola is calculated and used to calculate the total area. Each pair of strips will have an associated parabola. The areas under each parabola are summed to give an approximation of the area under the curve. Note that the more pairs of strips used, the better the approximation. The formula for Simpson's rule can be written as follows. H divided by 3 multiplied into the first height plus 4 times the sum of the odd heights plus 2 times the sum of the even heights plus the last height. Now let's work through the formula and see how it relates to the function f of x. Starting with h, this is the width of each of our intervals or strips as shown on the sketch and is calculated by subtracting the start of the interval on the x-axis, a, from the end of the interval, b, and dividing this number by the number of strips we want to use. The number of strips we can call n. In our example, we have 4 strips, and note for this to work, the number of strips must be an even number. Note the start of the interval a on the x-axis is now marked as x0, and the end of the interval b on the x-axis is x4 or xn. The first height is the one shown here, which we call y0 and labelled as first. So it's the value of the function f at x0, which is the start of the interval, also labelled as a on the sketch. Next, we want to look at what is meant by odd heights in the equation. The point to the right of x0 on the x-axis is x1. Its corresponding height is y1, shown here. As the number 1 suggests, this is one of the odd heights, and I've marked it with an O. Its value y1 can be obtained by evaluating the function at x1. The other odd height in our example is y3, shown here and marked with an O. This height is obtained by evaluating the function at x3. Let's look at what is meant by even heights in the equation. y2 shown here and marked with an E is an even height, as the number suggests, and can be obtained by evaluating the function at x2. Finally, y4 in our example is the last height referred to in the equation of the Simpson's rule, shown here, and is also referred to as yn. It's obtained by evaluating the function at xn, or in this case, x4, which is the end of the defined interval. The general form of the equation can be written as h divided by 3 multiplied into the first height y0 plus 4 times the odd heights, which range from y1 to yn minus 1, plus 2 times the even heights, which range from y2 to yn minus 2, plus the last height yn. Now let's apply Simpson's rule to a real problem. So we want to use Simpson's rule with 4 strips to evaluate the integral from 0 to 2 of 2 to the power of x dx to 3 decimal places. So now let's take a look at the graph of y equals 2 to the power of x in Desmos. So as you can see, it has an interval from 0 to 2, and I've created 4 strips, or 2 pairs of 2. Each of the strips as a width of 0.5, and we'll see how we get that value when we go back to the whiteboard. I've sketched the graph of y equals 2 to the power of x on the whiteboard. I've split the curve up into 4 strips across the interval 0 to 2 as the question asks. I've also put up a reminder of Simpson's rule. First, let's work out what the value of h is. We have 4 strips, so n is 4. H is the start point on the interval, which is 0 in this case, subtracted from the end point, which is 2. And the result of this divided by n. So we have 2 minus 0 divided by n, which is 0.5. To help us evaluate this, I've created a table. This is filled in with what we already know. So looking at the first row, we have n. This goes from 0 to 4 in steps of 1. The column labelled xn is the x-coordinate of each step, beginning at our starting value of 0 and ending at 2, our end point. The values in between are incremented by h, which we've calculated as 0.5. The next column, yn, is the height that we need to calculate. These are calculated by evaluating the function at the x-coordinate shown. The next column is the multiply sign, which relates to the formula. So the first and last heights at x equals 0 and x equals 2 are multiplied by 1. The odd heights, so that's at x equals 0.5 and x equals 1.5, are multiplied by 4. And the even heights at x equals 1 is multiplied by 2. The last column is the height, or the value in column yn, multiplied by its multiplier. So starting with n equals 0, to get the missing value in the yn column, we need to evaluate the function 2 to the power of x at the value of 0. So that is 2 to the power of 0, which equals 1. So if we multiply 1 by 1, we get 1. Now looking at the second row of the table where n is equal to 1, we see that the x-coordinate is 0.5. So we need to evaluate the function at 0.5. So the function is 2 to the power of x. So x in this case is 0.5 or a half. So when we evaluate the function, we get 2 to the power of a half, or the square root of 2. Now, because this is an odd function, we need to multiply it by 4. So we have 4 times the square root of 2. So y1 is equal to 4 times the square root of 2. So now moving on to the third row, where n is equal to 2. We need to evaluate the function at x equals 1. This will give us our y2 value, which is an even value or an even height. So evaluating the function at x equals 1, we get 2 to the power of 1, which is equal to 2. And because it's an even height, we need to multiply this by 2. So we have 2 multiplied by 2, which gives us 4. And now moving on to the fourth row where n is equal to 3, we want to calculate the height y3. So to do this, we need to evaluate the function at 1.5. So x is equal to 1.5. So it's 2 to the power of 1.5, or 2 to the power of 3 divided by 2, which is equal to 2 multiplied by root 2. As this is an odd height, we need to multiply it by 4. So it's 2 root 2 by 4, which gives 8 times root 2. So looking at the last row where n is equal to 4, we need to evaluate the function at x is equal to 2. This will give us the height y4. So the function 2 to the power of x, where x is equal to 2, gives 2 to the power of 2, which is 4. Now this is the last height, so it doesn't have a multiplier, so we can multiply it by 1, and this will give us 4. If we now sum the last column shown here, we get a value of 25.9706. Multiplying this value by the value of h, which is 0.5 divided by 3, we get our final answer of 4.328.